Okay, hello everyone, and welcome back. This is another recording of a lecture for PSY4050 Quantitative Research Methods. Okay, so I'm making a quick recording of the week 11 lecture. Hopefully get the timings right and it'll fit nicely within an hour. It's also, as with previous weeks, it's kind of useful supplementary material for people to be able to listen to this video and review stuff that we've had to rush through in the classroom lecture. Okay, so today we are covering multiple regression. Okay, so previous weeks we did linear regression. I'll do a little recap of that in a sec. But the aims are to introduce multiple regression, to consider the assumptions that need to be met when conducting multiple regression, and I'm going to outline the three main types of multiple regression: standard, hierarchical, and stepwise, and make various comments about which of those are better than others. Okay, so at the end of this week's lecture and lab class, you should be able to outline when to use a multiple regression analysis, evaluate when the assumptions underlying multiple regression have been met, and conduct multiple regression analysis and interpret the outputs. Okay. So firstly though, what I'll do is I'll do a quick recap of linear regression, the stuff that we covered in the previous week. So in week 9 we covered linear regression, where we had one predictor variable, one independent variable, and an outcome variable, a dependent variable. And those were the, if you remember, the independent variable, the IV, was the scores for that applied on the x-axis, and the dependent variable, the outcome variable, scores for that applied on the y-axis. So it gave us a series of coordinate data points for each of our observations, each participant. And we talked about modeling patterns in data using a straight line, and the regression version of the equation for a straight line, which is y equals alpha plus beta x. Quite commonly see it written like that, okay, where alpha is the intercept, or the value of y when x has a value of 0. So if we've got a zero value on the x-axis, what's the score on the y-axis there? And that's, you can see it highlighted on this figure. Alpha, that's the intercept point where the regression line crosses the y-axis effectively. And beta, that's the slope of the regression line. So how much the value of y changes for a 1 unit change in x, or a 1 unit change on the x scale. Okay, so in addition to this stuff, we also talked about residuals or errors. So the straight line is that we fit the regression line is a biased and imperfect model of our data, and there'll be some noise in our data around the line. So not all the data points will sit perfectly on the line, otherwise we would have a perfect model for the data. And the distance between the actual data points and the value predicted by the line represents the error. That's known as the residuals. A commonly used word for that is the residuals. As you can see, this was a slide from week 9 as well. Okay, and this raises the question of where exactly to fit the line. And we fit the line to minimize the residuals, minimize the errors, and we do that using the method of least squares. So the line is placed where it minimizes the sum of squared vertical deviations of the data points from the actual regression line. So what's known as the sum of squared residuals, and it passes through the coordinate that represents the mean of x and the mean of y. Okay, so this slide is just a bit of revision as well about the sum of squares. And if you remember, the deviations of data points from the line are squared before summing them, so that negative and positive deviances don't cancel each other out. And then what you do is you take those deviations from the mean value of y, and you square them, and you add them all together and gives you the sum of squares, gives you actual value. Okay, and then we pivot the line. The line gets pivoted around this point for the mean of x, mean of y, and software works out the intercept for us and the slope of the line for us. Save us having to do those calculations by hand, for which, if we did, we'd have to take partial derivatives and things like that. It'd get reasonably complicated, even for a kind of simple linear model like this with just one independent variable, one dependent variable. Okay, so we use linear regression to assess the association between two variables and whether we can predict scores on the dependent variable, the y variable, using scores on the independent variable or the x variable. Okay, so that's all stuff that we covered 2 weeks ago. Now, on to multiple regression. So, what if we want to do a more complex analysis and add more independent variables? So we want to add more predictors. We think that whatever our dependent variable is, whatever our outcome variable is, we think that more things may contribute to predict, may be useful predictors of that than just one variable that we've included in our model. So we want to add more IVs, more predictors, and look at the relationship between them and the DV and the extent to which different variables can be used to predict the DV. So which ones are better predictors of the DV? So we can extend this linear model by just adding further independent variables. And these additional x variables are just represented by additional terms in the regression equation. So you can see there the linear regression equation, y equals alpha plus beta x. For multiple regression, we're just adding additional terms. So we've now got y equals alpha plus beta 1 x1. So the slope of our first independent variable plus beta 2 x2. So x2 being our second independent variable. And we can continue adding them. Plus epsilon, which was, if you remember, that irreducible error term that sometimes it's written into the equation, sometimes it's left off. So here you can see I've added a second independent variable x2, which has its own slope relative to the dependent variable, but I could just keep adding further as required. Right, so just to unpack this a little bit more detail, it works in the same way really as the linear regression equation. Things to note here are that we still have an intercept alpha, just one intercept. There's only one place it crosses there's only one value at which our regression model crosses the y-axis when x is 0. But each independent variable has its own coefficient or slope relative to the dependent variable in the intercept. And you can see these highlighted. So in blue there, you've got beta 1. That's the slope of the line for the independent variable 1, x1. And the red, highlighted in red there, the slope of the line for the independent variable 2. So if we imagine we had a sample data set with two independent variables, such as in the previous equation there. So we've got x1 and x2. I've headed the variables, the columns, as x1 and x2 just for simplicity in this case. And the y variable is still our outcome variable. But here, if we had a data set like this, we'd have y is our outcome variable, our DV, and we've now got two predictor variables, two independent variables, x1 and x2, whatever they might be. And as I said, if each IV has its own coefficient or slope with respect to the DV, what does it look like when we try to visualize it? So when we have two independent variables, then we can represent it visually in 3 dimensions. So here we have an additional z-axis that I've added, which is, it runs horizontally in a similar way to the x-axis, and it kind of creates, these 3 axes sort of create what we could think of as like a 3-dimensional cube space. So by adding this extra z-axis, we've turned our 2-dimensional plot of x and y into a 3D cube with x, y, and z axes. And we can plot the data points as x, y, and z coordinates, axis coordinates, in a similar way to what we did previously, where each data point is now in a 3D space, and it represents a score. Each data point represents a score on the first independent variable, x1, mapped onto the x-axis, a score onto the second independent variable, x2, mapped onto the z-axis, and a score on the dv, still on the vertical y-axis. Yeah, and what this does to our fitted regression line is it turns it into like a 3D surface or plane, as I've tried to represent here in this image. So if it was two-dimensional, we'd just have kind of one straight kind of orange line to represent our regression line. But now that regression line in 3 dimensions has become like a flat surface. And that's what that kind of orange kind of square shape is meant to depict. It's the shape of what we could now call maybe the regression plane. And it's important to note that once you go above 2 independent variables, you've gone beyond 3 dimensions. And I can't represent that visually, so I don't know how to draw something that's more than that has more than 3 dimensions. Yeah, but despite the fact that we can't visualize it, if we have more than 2 independent variables, so if we added a third or a fourth independent variable, we wouldn't be able to draw a plot of it like this. Despite the fact that we can't do that, we can still solve for the coefficients mathematically using the least squares method. Okay, so apologies, this slide has lots of text on it. Couldn't think of a way to convey this information in a more interesting or different way, but I'll just read what it says. It says, despite the fact that we can't visualize it, we can keep adding predictor IVs to the model and mathematically solve for the coefficients or slopes. And the goal is to arrive at a set of beta values or coefficients, regression coefficients, that bring the predicted y values as close as possible to the actual y values in our data set. So it's same procedure really. We're doing least squares regression, but we're doing it with lots of independent variables. And r squared in a multiple regression model is the proportion of variation in the dependent variable that is predictable from the best linear combination of the independent variables. So you'll remember from linear regression, SPSS, it gave us like 3 different tables. One of those tables was the model summary table, where it gave us r squared and adjusted r squared, so we were able to use those to understand how much variation, how much variance had been explained by fitting this model, how much we were able to explain the outcome variable by looking at by using the predictor variables or the predictor variable that we had included in our model. Okay, so the more independent variables we add to the model, the more variation the model would explain. Okay, so just adding variables will increase the variance explained, but may not necessarily improve the model. And we'll see how that works as we go through. Yeah. So variables may not be significant predictors of y and may not contribute to the model. We'll see that when we run some of these models, where we look at how much r squared changes when we add new variables to the model, and whether it's significant or not. Okay, so an important point to remember is that simpler models are often preferred if we've got a model with 2 independent variables and 1 dv, and a model with 4 independent variables and 1 dv, and there's no significant difference in the amount of variation explained, then we should prefer the simpler model with 2 independent variables, because it explains as well as the more complex model, but it's more parsimonious, and will be easier to interpret. Okay, right, so there are two important stages to running a multiple regression analysis. Firstly, we should check the data that we're using matches the assumptions for multiple regression model. Okay, so we call that checking assumptions. There are quite a lot of things to check to make sure that you are not erroneously running multiple regression on data that's not suitable. Yeah, and the second is to choose an appropriate method of multiple regression modeling, and there are three main types: standard, hierarchical, and what's known as statistical, of which stepwise is kind of the most common. I'm going to make various comments on these as we move on. Okay, but firstly, I think we need to look at data assumptions. So before you run any analysis, as you know, you need to make sure your data meets the assumptions so that you're not getting erroneous results and you are actually modeling the thing you think you're modeling. So like with some of the previous analyses we've run, such as ANOVA, where the data had to meet assumptions of normality and homogeneity of variance, with multiple regression, there are a number of assumptions we have to check to make sure we're not producing erroneous results from our analysis. There are 6 for multiple regression, really, 5 that are really key. The last one is a little bit sample size, a little bit more tricky, I think. These are normality, linearity, homoscedasticity, independence of errors, outliers, and the sample size. Okay, so we'll work through these one at a time. So normality, this basically means that the residuals should be normally distributed about y. What we'd say you call y hat, or the predicted DV scores. And the residual scatter plot. So when we run our analysis, we can ask SPSS for these sorts of residual scatter plots, and they should show a nice rectangular and symmetric distribution around 0. So the horizontal 0 line on these plots is our reference point, and we're looking at standardized residuals here effectively. And when we kind of eyeball these to see what's going on, what we want to see is a nice symmetric distribution above and below the line 0, the horizontal 0 line in those residuals. So you should be able to pretty much draw like a rectangle around them. So you can see here there's 2 plots for comparison. In the first one, the assumptions have been met. There's as much kind of variation above the line as below it in that first image. If you look at the second one, there's a lot of data points spread out below the 0 line, and then there's a load that are clustered very close to the 0 line above it. So that would be a failure of normality. The data isn't normally distributed in that sense. It's going to be skewed in some way, if you can visualize that to some extent. So yeah, it's eyeballing these things is a useful way to get an idea of how your data's looking. Okay, so secondly, is linearity. So we're fitting a straight line model to the data. So if the data doesn't follow a pattern that it can be represented by a straight line, then we're making a mistake. Okay, so we're assuming there's a linear relationship between the residuals and y hat, the predicted y values. Okay. If we don't find this, it doesn't invalidate the analysis, but it weakens the analysis, and we may find we have to add additional terms and effectively convert our model from a straight line model to maybe a quadratic model by adding exponents to some of the independent variables. We're not going to worry about that at the moment. So, but as it says here, it could be necessary to transform your independent variables, such as by squaring them. So if we look at this image, if we've got this nice rectangular symmetrical pattern above and below, the reference line of 0 with the assumptions have been met, similar to the normality issue. It looks like the data is linear. The residuals are linearly distributed. If you look at the other one, you've got this weird different shape where at low values, low predicted y values, the residuals are below 0, and at high predicted y values, the data is below 0. But in between that, the data is above the 0 line. The residuals are positive. So that would be starting to look like a parabola, so like an inverted U shape. And in order to model data that look like that, you would probably need to add independent variables that didn't follow a linear pattern, such as quadratic or quadratic variables. That would be you'd have to square your x variables. And that becomes problematic because then what you're actually analyzing is transformed squared variables and not the variables you collected. So you have to take that into account when trying to explain what's going on. Okay, so the next one, homoscedasticity. A Greek word apparently means constant variance, and this is the assumption of constant variance. It's similar to the assumption of homogeneity of variance if we had grouped data. But here, remember, we're looking at continuous scores. And it basically means that the standard deviations of our residuals are equivalent for all the predicted dependent variable scores, the predicted y hat scores. Yeah, and departures from this assumption tend to be funnel shaped. So if you have this sort of pattern in your data, it doesn't invalidate the analysis, but it weakens the analysis. And transforming your variables may help again. Okay, so looking at that image, you can see the same sort of thing. Nice symmetric distribution. It means this assumption's been met. But that would be homoscedasticity. The variability above and below the line is about equal all the way along the scale on the predicted y axis, all the way along. If we look at the opposite way, the assumptions haven't been met, what's labeled as heteroscedasticity. So it's variance that isn't constant. We've got at the low end of the scale, we've got very little variation, very little variance above and below the line of 0. And then as we go up the predicted y scale, you get this funnel shape and you get loads of variance of both above and below the line, so it looks like a funnel. Okay, so independence of errors, that was another one. The fourth of our assumptions to check. So what this means is that for any two observations, the residuals should be uncorrelated. They should be independent of one another. And there's a useful statistic we can use to kind of measure the extent of correlation of errors across the cases in our sample. And SPSS will give us, we can ask it for this Durbin-Watson statistic that measures the extent of correlation of predicted errors across the sequence of cases in our sample. And as a rule of thumb, the result should be, the Durbin-Watson statistics should be between 1.5 and 2.5 for each of our residuals. If we find it is between those values, then we know our errors are independent, and we're pretty safe with our analysis. Okay, so this is kind of a quick summary of the images on the previous few slides prior to me talking about independence of errors. just gives you an idea of what the different scenarios look like. The first one, we've got this nice symmetrical pattern above and below the reference line of 0, or residuals plotted against our predicted predicted value of y. If we've got a failure of normality, we might find something that looks a bit skewed, where all the data points are clustered close to the line and far away from it below the line. Could have been the other way around. It could have been the ones below the line could have been clustered close to it. When we're looking at non-linearity, you can see that isn't a straight line. If you look at the way those data points, how they change as you move along the predicted y values. And then the final one, heteroscedasticity, where we want our variance to be constant all the way along the scale, and in this case it isn't. There's greater variance at one end of the scale compared to the other. Okay, right. So outliers are important things to consider. So we've got two types of outliers: the univariate outliers. And we have to consider these because they, as when we talked about linear regression, as you know, if you've got an outlier, because of the way the regression line is fitted, an outlier will, in any direction, will pull the location. It will pull the line down or up. It'll affect the slope. It'll have an undue influence on the slope. And there's a statistic we can use to look at to look at whether we've got any univariate outliers, and that's what's known as Cook's distance. And we can ask SPSS to get this for us as well. And then we can, if we identify we've got using Cook's distance that we've got any kind of any outliers that might be a bit too influential and influencing the regression line, the location of the regression line, too much, we can remove them from the analysis and then run it again. Multivariate outliers, it's a little bit more complex, but it's the same sort of thing. We can use something called Mahalanobis distance, so a statistic known as the Mahalanobis distance, and it works in a similar way to Cook's distance. It identifies certain thresholds for what is and isn't an outlier, and then we look to see if we've got any scores that sit outside that are more extreme than that threshold, and we can remove them from the analysis. Multivariate outliers it's quite a complex thing to explain, because when we're talking about multivariate, we're talking about multiple variables. So these are outliers across more than one variable, essentially. So univariate outliers would be a outlier on any individual variable. A multivariate outlier would be it's an outlier on more than one of our independent variables combined. Okay, so we'll have an undue influence on our model unless we deal with it. Okay, so sample size, power and effect size. So for sample size, this is kind of a bit more tricky. The others are sort of more straightforward. We can look at plots, we can look at certain statistics that help us to make a decision. But for sample size, I think it's often the case that you're stuck with whatever sample you've got when you're conducting research. But in terms of calculating how big a sample you need, Tabachnik and Fidel, whose multivariate statistics textbook is recommended reading for this course, is a very good book. They suggest the following rule of thumb, assuming you're looking to detect a medium-sized relationship. So we're looking for a medium effect size, medium-size effect of an R squared of about 0.15 or about 15%. So that would mean we have enough sensitivity to be able to detect a significant result that represents a medium-sized effect. The bigger our sample, the more ability we will have to detect significant relationships that represent a small effect size. Not necessarily the case that we need to do that. So that's it. So their guidelines, their rule of thumb is if you're looking to detect a medium-sized relationship, R squared is roughly about 0.15 with a alpha or a probability significance level of 0.05 and a power of 0.80. So remember, power would be like the type 2 error issue. We don't want our study to be underpowered, but we don't want to be rejecting results that could be significant. Okay, so they recommend that your sample size n should be greater than or equal to 50 plus 8 times m, where m is the number of predictors or the number of independent variables. So if you had 2, that would be 66. So if you had 2 predictors in that first calculation, that'd be 50 plus 8 times 2, so 50 plus 16 would be 60. You'd need 66 participants. Okay. Alternatively, you could use the second formula where they recommend 104 plus m. So 104 participants plus, if you had 2 predictors, 100, that would give you 106. Okay, and you should apparently always pick the larger n calculated using both methods if you're interested in the significance of individual predictors. Is what they're recommending here. So this is an old-fashioned way to do it. And that's not necessarily a bad thing. You don't often see these sort of sample size calculations done by hand. It's not necessarily a bad thing to do that, though. But one of my issues with this is sometimes you're just stuck with the sample size you can get, essentially. Certainly when it comes to getting people to take part in research, and certainly in disciplines such as psychology. Okay, so there are more sophisticated calculations involving estimates of likely effect size for an analysis, so a power analysis, and these are as follows. What we'll do is get R squared from the literature or use our own preferred value. So if we're doing research on a particular topic, what they're suggesting here, this is from the Tabachnik and Fidel textbook, they're suggesting you kind of have a look through the literature and see what sort of measure of effect, what sort of R square value similar research in this particular area is reporting. Yeah. And then you kind of use that to get an estimate of what size effect you should be looking for and what kind of sample size you should be looking for. And you can use this calculation here. So first, calculate an anticipated effect size using Cohen's F. And that is the second formula there. So it's like F squared equals R squared. So we know what that is. That's a figure we can. In this case, we'd have had a look at other articles that are doing research in a similar area on a similar topic to us, looked at their kind of effect size they're reporting, and we'd have taken that. We'd take that, then we divide it by 1 minus R squared, and then once we've got F squared, we substitute it into this equation that's shown underneath, which is to get our sample size n, it needs to be greater than or equal to 8 divided by our answer for Cohen's F squared, and then add m minus 1, where once again m is the number of predictors. So if we had 2 independent variables, then m would be 2, so it would be 2 minus 1 or 1. Okay. A thing to note here is if your outcome variable, your DV, is not especially normally distributed, so your outcome's you're not got a normally distributed dependent variable, then sample sizes need to be even bigger. And similarly, if stepwise variable selection is used, much bigger samples are required. I will come on and describe stepwise when we talk about the different types of multiple regression. I'll talk about stepwise shortly, but for stepwise multiple regression, Tabachnik and Fidel are suggesting a 40-to-1 ratio of cases to independent variables. So for each IV you've got in your model, you need at least 40 participants. Okay, so if you had 2, you need 80. okay, to avoid the problem of your chosen solution being sample specific. Okay, and it says there at the bottom of this slide, that be wise, don't use stepwise. I'll say more about that in a second. We've got standard, hierarchical and statistical multiple regression. Stepwise is a form of statistical multiple regression, and it's not one that is recommended. We're going to sort of explain what it is to you so you understand what it is, but it's not one that people use routinely. It's not kind of highly recommended. All right, so those are the 6 things we would need to check, and in the lab classes we'll be spending some time learning how to check those assumptions. It's pretty much just following various steps, and we'll be using like a regression map to do that. So kind of like a map that outlines the different steps that we go through to check these assumptions before we run our analyses. It's kind of a map created by Jonathan, and it's pretty useful. So once we have checked all those assumptions and met all those assumptions, then we need to decide how to run a multiple regression analysis. As I said, there are 3 types of multiple regression. This figure illustrates how some variables are correlated, and we're going to use it over as I talk about the different types of multiple regression to understand how the different ways of running these analyses influence the variance that's attributed to different variables. So what you can see here is we have a DV. Each circle represents a variable. The circle labeled DV is our dependent variable, and we've got 3 independent variables represented by circles, and they overlap, and the degree of overlap represents the extent of correlation between the independent variables and the dependent variable. And remember, when we talked about correlation, when you look at the extent of correlation between the 2 variables, it's the amount of variance that they share, essentially, and that can be captured in this sort of figure by the extent to which they overlap. So, for example, A is equal to it's the variance explained, or the correlation between IV1 and the DV if we control for the other variance explained that's not unique to it, to IV1. So the area that's covered by B, which it shares with IV2. Okay, and B, the area B is shared correlation with the DV between IV1 and IV2. Okay, so it's the amount of overlap between IV1, IV2 and the DV. Right, so we're going to use a figure like this to understand how the amount of variance that's attributable to individual independent variables changes when we do different types of regression. And there are 3 main types of multiple regression: standard, sometimes called simultaneous; hierarchical, sequential, where we add our variables sequentially to the model; and stepwise, statistical, where we use statistical we use statistics or some sort of statistical justification for the order in which we enter our variables into the multiple regression model or the analysis. And the differences influence what happens to the overlapping variability due to the correlation between the IVs. And the methods differ in who decides the order of entry of independent variables into the analysis. Okay, so let's start with standard multiple regression. So this is the most common. It's the one that I would recommend using more than any other. And in this case, all independent variables are entered into the equation at once. And then each independent variable is its contribution the amount of variance it shares with the DV and its contribution to the model is assessed as if it had been entered into the equation after all of the other independent variables had already been entered, and their contributions had been kind of controlled for. So each independent variable here has been evaluated in terms of what it adds to the model after all other IVs have been taken into account. Okay, so this figure kind of illustrates that. If for this particular model where we've got 3 IVs and a DV, if we did a standard multiple regression on this, then what we'd find is IV1 contributes variance that's accounted for by A. So IV1 gets A, it contributes the amount of variance there, the amount of overlap with the DV that represents that area that's labelled A, that's highlighted or shaded. IV2 contributes that small area there in the middle called C. So using standard multiple regression, it's only contributing a small amount to the model once we control for or take into account what the other independent variables have already explained. And IV3 contributes this area that's labelled with the letter E. Okay, so that's standard regression. Effectively, you put all your variables into the model at once, simultaneously, and they're all treated. Each one is assessed on its unique contribution. If we took out the overlap it shares, the stuff that's explained by its overlap with the other variables, with the other independent variables. Okay. Hierarchical multiple regression is slightly different. In this case, independent variables are entered into the model in an order specified by the researchers, so that can be useful. And then each is assessed in terms of what it adds at its point of entry. Okay, so the researcher will often assign the order that they input these variables based on theoretical reasons. So if you're doing some research, you know your topic well, you know that certain variables are meant to be good explanatory variables, you might want to put those in first and then see what other variables contribute beyond those. Okay, but if we do a hierarchical regression, it changes. If we entered the variables for this particular model in the order IV1 first, IV2 second, IV3 third, for whatever theoretical reason that might be, this time what we find is that independent variable 1, IV1, contributes the area that's covered by both A and B. So the amount of variance explained by that variable, it now is contributing more to the model by using a slightly different method for running the analysis. Yeah, and IV2 this time contributes the area that is represented by C and D, so it's getting more variance attributed to it, so it's making a bigger contribution to the model than when we did standard regression. And IV3 in this case contributes the area that's labelled with the letter E. Okay, so you can see how that's changed. IVs 1 and 2 are accounting for a much bigger area they're contributing more to the model. They're accounting for a bigger area of overlap of correlation than when we did the analysis using a different method. Okay, so notice how that's changed from standard multiple regression. Okay, the third one is statistical, or sometimes most commonly referred to as stepwise multiple regression. And in this case, the order of entry of IVs is based solely on statistical criteria. Okay, and the IV that has the highest correlation with the DV is often entered first, and then so on and so forth. Okay, and how does this affect the model? Well, we get different results if we do a stepwise analysis. So what we find is, if we did a stepwise analysis based on correlation, we know which variables are most highly correlated with the DV, because with C they've got the greater amount of overlap with the DV. Okay, and what we find is that IV1 only contributes the area accounted for by A to the model. IV2 contributes the area accounted by B and C to the model, so that's changed from when we did it hierarchically or stepwise. And IV3 now gets both D and E, so it's gone into the model first because it's got the highest correlation, and it's now coming out as a bigger contributor than it was previously. Okay, so when you're doing statistical regression, as I said, the most common term you'll hear it referred to is stepwise regression, but there are actually 3 versions of statistical regression. There's what's known as forward selection, where IVs are added one at a time based on the correlation. There's backwards deletion, where you put everything in and then IVs are removed one at a time based on the extent to which they correlate. And then there's stepwise regression, where IVs are added one at a time, but can also be removed at any step if they no longer contribute to prediction. So by maybe you've added IV1, then IV2, and when you add IV3, you find that IV2 is no longer a significant predictor, so you could remove that from the model. The general, as I said to you previously, the general view is that statistical regression is not a good idea. It's not a sensible way to do things. Standard regression is the most common way things are done. Hierarchical regression is also commonly used if you've got good theoretical reasons for entering one variable into a model first, or if you want to look at how something changes, having control for a couple of other things. So decisions based solely on the size of the correlations in the sample are not a sensible way to approach this. So, for example, which variable would go in first of 2 that have very similar correlations? So in this case, R equals 0.456 or R equals 0.457. Using statistical regression, you'd put the second one in first, even though it's marginally more highly correlated, but it's gone to like the thousands. It's gone to the 3rd decimal place already. And SPSS will, if you did stepwise like this, if they were almost identically correlated, it would go to the 7th, 8th, 9th decimal place to identify which was just slightly larger. And also, as a researcher, you should have some idea about the importance of your predictors based on theory. Okay, so if you don't, then do a standard multiple regression. If you've not got theoretical justification for using this kind of method, then do standard. Okay, I think we're nearly finished here. So, in summary, so we use multiple regression in an attempt to predict dependent variable scores, the scores on a dependent variable on the basis of more than one independent variable. So we've got multiple independent variables, multiple predictors, and we're looking to assess which are significant predictors. Yeah, and we might find we have a good model, and when we look, not all of them are significant predictors. Assessing data assumptions is important. It's an important first step. We're going to check our data assumptions. That's something we're going to do in the lab class. We'll go through that exercise. It takes a little while, but we'll go through it, check we've got our assumptions right before we start running any analyses. Okay, and standard and hierarchical regression are the things, they're the analyses we'll run in lab classes. So we'll run a standard multiple regression. I don't know why on this slide I've called it simple. It should say standard. I shall edit that. But in the lab class, we'll run a standard multiple regression on some data, and we'll run a hierarchical multiple regression as well, where we kind of end up with more than one model because we've added extra variables. But we're not going to do statistical regression. We're not going to do stepwise regression because it's not necessarily, it's not a particularly good idea to do. Okay, just need to be aware of it, but the two we're going to practice in lab class in our worksheets and exercises are standard and hierarchical. Okay, so the references for this particular lecture on multiple regression are, if you look at the most recent version of the Andy Field textbook, chapter 9 covers regression generally, starts off with linear regression, then goes on to consider multiple regression, extends it to consider multiple regression. The second one on there is the Tabachnik and Fidel textbook. It's shown as 2014 on here. I think the most recent edition was 2014. It's called Using Multivariate Statistics. It's an excellent textbook, and it's chapter 5 in the 2014 edition. If you find a different edition or an older edition, I've got an e-version of a new edition and a hardback version of an older edition, and the chapter numbers might be slightly different, but yeah, you just want the chapter on multiple regression, and that's a really good statistics book for multivariate stats of the type that we're going to be talking about over the forthcoming weeks on this module. Okay, so I feel like I've talked for long enough on this. And so I'm going to stop now, and I see you guys in lab classes. I'll see you guys in the actual in-person lecture and lab classes. Okay, cheers, bye.